Hello everyone, my name is Nate, and today I will present to you our work titled Symmetry and Uncertainty-Aware Object SLAM for Sixth-Off Object Pose Estimation. This work is a collaboration between the University of Delaware, Bosch, and TUM University. This work addresses the need for real-time, multi-view, and multi-object sixth-off pose estimation. As you can see here in the video, we want to track the 6 degree of freedom pose of multiple objects at the same time, all in real time. The key contributions of this work are a keypoint-based object SLAM system that explicitly handles the symmetry of objects, such as the bowl that you can see here in this figure. We also accurately quantify the uncertainty for semantic key points and show that it is accurate in experiments. Let's give a brief overview of our system. First, our system expects image and bounding box inputs. The objects are split between asymmetric and symmetric objects, with the asymmetric objects being processed first. As you can see here, we send the images cropped at the bounding box to our keypoint network, which can predict key points as well as uncertainty. The key points U and uncertainty sigma are sent to a front-end tracking module which estimates the current camera pose and inserts it accordingly into the 3D scene. Now with the current camera pose, we reproject 3D key points for symmetric objects into the current image in order to create prior key points, as you can see here. Just like before, we can now predict key points and uncertainty, but this time, they are consistent with the 3D scene for symmetric objects. Our system periodically runs a back-end graph optimization to jointly refine the entire scene. This is the overview of our Symmetry and Uncertainty-Aware Object SLAM, or SUO-SLAM system. Let's talk a bit more about how we perform keypoint-based SLAM for symmetric objects. In keypoint-based SLAM, we typically need 2D correspondences to static 3D points. But if you think about it, this cannot be determined over time with symmetries in the objects and a lack of texture. Our idea is to project object key points from the 3D scene to create keypoint priors, which allow the network to predict key points that are consistent with the 3D scene. As you can see here on the left, the keypoint priors are projected into the image, sent to the network, which can then predict key points which are consistent with the 3D scene and rotating correctly as seen here in the center of this video, which leads to the good pose predictions on the right. In summary, the prior detection allows us to reliably track symmetric objects over time using the semantic key points. Let's go into a bit more detail about our keypoint network. As we mentioned before, the network takes in an image with a prior detection input for each key point. Then, predicting a spatial softmax tensor P, we can predict key points U and uncertainty sigma that is differentiable and pretty reasonable, as you can see here on the right. The key points and covariances are jointly regressed in a Gaussian maximum likelihood estimator loss, as you can see here. This loss enforces the covariance to tightly bound the true prediction error while also enforcing that the key points are close to the ground truth. We first tested our system on the YCB video dataset. Here you can see that SUO-SLAM beats real-time state-of-the-art that also uses a single model for all objects. Our front end can run at 11 Hz on keyframes, while our back end runs at 2 Hz. On the TLIS dataset, we show competitive accuracy with the real-time state-of-the-art, while also providing consistent poses for symmetric objects over time. We also show that multi-view fusion, keypoint priors, and learned covariance are crucial to achieving these results. Let's go into some details about the output of our system. As you can see here are two views of the output of our system. And as you can see, due to the prior detections, the key points are consistent in the second view with respect to the first view. That is, they look like the same key points, just rotated, as we would expect. When we run the same system, however, without the prior detection, the key points are now not consistent or inconsistent with the first view, and thus, fusing them over time, SLAM fails. In summary, we presented a symmetry and uncertainty-aware object SLAM, or SUA-SLAM system. It's a keypoint-based object SLAM system that explicitly handles symmetric objects. And we provide a semantic keypoint network that predicts accurate uncertainty. Our code is available, as you can see here, and we would welcome you to reach out with any questions. Thank you for your attention.